Let's delve into the concept of mutual exclusion, a crucial aspect of operating systems. This principle ensures that shared resources are accessed by only one process at a time, preventing conflicts and maintaining data integrity. We will explore how mutual exclusion is achieved and why it is essential for concurrent systems. So, what exactly is mutual exclusion? It's a property that guarantees that only one process can access a shared resource or a critical section at any given moment. Think of it like a single key to a room. Only one person can have the key and be inside the room at a time. This prevents what's known as race conditions, where multiple processes try to modify the same data simultaneously, which can lead to data corruption. In essence, mutual exclusion maintains data consistency in concurrent systems by ensuring exclusive access. Now let's focus on the critical section, which is a code segment that accesses shared resources. It's imperative that this section is executed by only one process at a time. Consider a scenario where multiple processes are trying to update the same bank account balance. Without proper protection, the final balance might be incorrect. To prevent this, each process must request permission to enter its critical section, ensuring exclusive access and preventing data corruption. Here is a simple illustration. In the while loop, there is an entry section, the critical section where a shared resource is increment, and the exit section which releases access. Finally, it goes to the remainder section and performs other actions. To effectively implement mutual exclusion, certain requirements must be met. Firstly, mutual exclusion itself. Only one process can execute in the critical section at any given time. Secondly, progress. If no process is in its critical section and some processes want to enter, only those processes not in their remainder section can participate in the decision of which will enter the critical section next. Thirdly, bounded waiting. There must be a limit on the number of times other processes can enter their critical sections after a process has requested to enter its critical section. Lastly, no assumptions. No assumptions should be made about processing speeds or the number of CPUs. The solution should work regardless of hardware configuration. These requirements ensure that mutual exclusion is implemented fairly and efficiently. Let's explore software-based solutions for achieving mutual exclusion, and we'll begin with Peterson's algorithm. This algorithm is a classic software solution designed for two processes. It ensures mutual exclusion without relying on specialized hardware instructions. It utilizes two variables: a flag array, where each element indicates whether a process wants to enter the critical section, and a turn variable, which indicates whose turn it is to enter. Peterson's algorithm satisfies all three key requirements: mutual exclusion, progress, and bounded waiting. Here's how process I utilizes these shared variables, along with an entry and exit section. First, the flag for the process I is set to true, then the turn is set to J. Inside a while loop, it checks the flag and the turn to take action. Now, let's explore hardware-based solutions for mutual exclusion. First, we have the test and set lock or TSL instruction. This is an atomic hardware instruction that tests and sets the value of a memory word. In essence, it checks if a lock is available and, if so, acquires it in a single, indivisible operation. While TSL offers a simple implementation, it suffers from busy waiting, also known as a spin lock, where processes repeatedly check the lock status. Next is the compare and swap or CAS instruction. This instruction atomically compares the contents of a memory location to a given value and modifies it only if they match. While CAS is more flexible than TSL, it still relies on busy waiting, which can lead to wasted CPU cycles. Semaphores are synchronization variables with an integer value that are accessed through two atomic operations: wait, also known as P, which decrements the value, and signal, also known as V, which increments the value. There are two main types of semaphores: binary semaphores, which can only have a value of 0 or 1, and are equivalent to a mutex lock, and counting semaphores, which can range over an unrestricted domain, and are used to control access to resources with multiple instances. Now, let's examine a basic semaphore implementation. Semaphores are a structure with an integer value and a process queue. The wait operation decrements the semaphore value and blocks the process if the value is less than 0, adding it to the queue. The signal operation increments the value and wakes up a blocked process, removing it from the queue. Monitors provide a high-level synchronization construct. A monitor encapsulates shared data and procedures within a module, ensuring that only one process can be active inside the monitor at any given time. This construct offers automatic mutual exclusion for monitor procedures, employs condition variables for process coordination, and is generally easier to use than semaphores. Now, let's examine the classic bounded buffer problem implemented using a monitor. Within the monitor, there are procedures for depositing and removing items from a buffer, along with condition variables to handle full and empty buffer states. This implementation elegantly handles mutual exclusion and synchronization, making it a powerful tool for concurrent programming. In summary, mutual exclusion is crucial for preventing concurrent access to shared resources. Critical sections must be protected to maintain data integrity. Solutions must satisfy mutual exclusion, progress, and bounded waiting requirements. Both software and hardware approaches exist, and understanding mutual exclusion is essential for concurrent programming. Now let's review some of the key concepts, implementation approaches, common issues, and best practices for achieving mutual exclusion effectively. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.